Okay, welcome everybody, and good afternoon or good morning, depends where you are between the US and Europe, and maybe some people in Asia as well. Good morning there. We basically are going to cover the subject of what is AME, additive manufacturing electronics, and the impact that we see on the industry and the industry roadmap for the electronic circuits and devices. I just want to let everybody know there is a poll that you can fill a few questions, like which industry you are from and other information there. We'll appreciate if you can fill it up as well. So the subjects I'm going to cover today, or basically the agenda for today, just a second, we'll get the mouse working here, is what is AME, examples of functional AME devices. So you can see what can be done, and this is just some examples, there is way more. The electronics industry roadmap and where technology will go with this as it applies to the industry roadmap. The direction that the AME fabrication technology can allow the engineers and the circuit designers and application designers to work on. So if we look at the electronic circuits in general, so far they have been divided between the basic integrated circuits in semiconductors, and then the integration of those package devices into the printed circuit boards for making the products that we look and use today. However, as the technology evolves and all that, we see the need to basically introduce the additive manufacturing electronics that, as we will see, basically serves as a bridge between the integrated circuits and the PCB technology. And we will see how these things basically will merge into a single type of a device structure. And that's the direction basically that the industry it's tending to go. So the additive manufacturing electronics, basically today, the most commonly known AME is the surface conductive deposition, or traditionally known as printed electronics, where you get a deposition of a conductive trace, primarily silver, in some cases also some copper based on screen printing, for example, from a very heavy paste, either in a single surface or dual surfaces. And what the other technology that it's in the evolution, where actually Nano Dimensions specializes primarily, is in the multi-layer and dielectric and conductive deposition. And this basically brings the ability to create different structures, like a multi-layer electronic device. This is an X-ray of a 7-layer system with where you can see also the vias. And the unique thing here is that you have a simultaneous formation of the dielectric and the conductive layers. And we'll see that in a few slides more clearly. What this technology allows also is to create different types of structures, which are almost complete electronic circuits. In this particular example here, this is about 8 millimeters in diameter, 3 millimeters in height. Has some capacitive coupling plates printed in there, and then mounted a BGA that includes the driver for the wireless communication as well as the signal processing, some passive components, and then we can see there the coil for the RF communication as well as the socket for a battery. And this basically makes a complete system for sensing in a particular medical application, things on the human body, and wireless communicating that to the receiver for analysis and further notification to the doctors or whoever, whatever is being tested there. That's just one example of what can be done here, from the traditional kind of 2D, 2.5D into the type of 3D structures. So if we first try to understand the difference between the printed circuit board, the PCB technology, and the AME, as we know, the PCB is an analog process. It's a lamination, pattern, etch, pressing, and electroplating sequence of steps. A very complex process after all. It has evolved over many, many years, as we know. And AME, in contrast, is a single body built from the bottoms up with a single dielectric body continuously, and the traces of the metal in between. And if you desire, you can have all the vias filled up by the same process. It's a digital process. There is no lamination, no patterning, and electroplating could be optional, depends on what the customer is trying to do. Some cases, some electroplating is done to make it more compatible with some different environments, such as the human body, blood, and so on, where the traditional the traces of silver or even copper will not be compatible with. So that's the situation with respect to, and a clear difference between the AME and the PCB technology. And more important is that being a digital process, you can create any shape vias. They can be round, they can be in any angle, as well as, of course, the traditional 90 degrees vertical vias. And they can be varied vias, micro vias, full via. And basically here, the designer has the freedom of designing whatever he wants because it's a fully digital process. So AME simplifies the complex electronics manufacturing process, and this is very important to understand. So on the top side of this picture, we see the traditional process of PCB technology, which basically what you have here is more than 70 steps to make the PCB, and this doesn't include the assembly part of it. And then it's not an environmental friendly process. You have a lot of chemical waste, as well as it's an energy hungry process. Compared to the AME, which we see here under the new process line, which basically is just one machine produces the entire circuitry, and it can hopefully not too distant future also does the assembly, and then you just do the testing and ready to ship basically. So dramatically reduces the chemical waste and reduces the energy consumption altogether. Sorry for the typos there, we need to fix that. So this technology basically not only is more efficient in the process and the technology and the capabilities of design, but also from the environment point of view as well, and the energy consumption. So from CAD to a digital fabrication file, how do we do that, and what's the implication that we see here? So we have the ECAD or mechanical CAD designs that where the AMEs can be done. Then basically you use either of some of these standards like the IPC 2185 with the outputs of ODB++ or Gerber, Excel, and STL files. And you basically go into what is called a vector in a Gerber file, which then the system translates that to pixels in a digital file. And this is probably one of the key issues that need to be taken into consideration when designing, for us designing the equipment, but for the system that converts these, make sure that everything is aligned to the pixels. And why is that? As we have the vector, basically, if we can have everything within the pixels or off the pixel, and this is the issue that basically the rendering system takes care to make sure that everything fits within the pixel, so we get a perfect shape and no variation in the design tolerances and rules that could create a line that could be broken or not completely straight. So the technologies for AME fabrication include inkjet, which is the most common, and we'll see some things, dispensers such as aerosol, laser direct structuring, which converts a liquid into a solid. That's in a very early stage in the AME field. Extrusion is also another possibility, but it's also not that popular, or it has some limitations there. And upcoming, not too distant future, we'll probably see laser-induced forward transfer, lift, as another way of depositing materials. And basically it could be at the end a combination of different sources depending on the type of the structure that is being built, the complexity of the circuitry, and what is required. We can see systems that may have inkjet and lift, or aerosol and lift, or a combination of more than one or two technologies. So the single material digital fabrication, typically, which is done with aerosol or dispensers, you have your digital print file, and you direct the ink or the nozzle to basically deposit the material in the substrate per pixels, and you get basically a picture that has some dots basically per the deposition there, and you connect on them. The process that this has probably the minimum roughness is a relatively typically a smooth surface compared to others, compatible with over 3-axis robots, so it's something that allows to create a very popular antennas on any surface, so sometimes a curve, a dome, and things like that. And easier thickness management in the slots, typically because you rotate the printer head itself, the nozzle. In the cons, basically, it's a very low throughput. Thickness is limited to the speed and ink viscosity. And at the end, you can have a material tail due to the on-off of the ink itself. The other technology is the multi-material digital fabrication, where when you have your design file, where you have your metals is shown by the gray areas, and then you have two nozzles, one for the dielectric and one for the conductive layer, and you create, for example, you start creating both films there, and then you build up to the height, and basically you simultaneously start building up the multi-material to create the desired structure, as we show in that schematic of the difference between AME and the PCB. So in the process is a high throughput, unlimited thickness, simultaneous multi-material, and it's a clean on and off deposition because you control these nozzles very effectively and very fast because there is basically drop on demand. The cons could be the trace roughness. However, the suppliers of equipment based on ink, they are working on algorithms and materials to minimize this and hopefully eliminate that, that effect. So here are some examples of the material digital fabrication where we can see a close look into both the conductive layer on the left-hand side as well as the dielectric on the right-hand side. And these materials basically are simultaneously deposited, as we mentioned before, and sintered as well as to form the electrical device. And we'll see exactly how it's done shortly. So the digital fabrication basically usually has a 1 pixel tolerance, and let's see what the impact is of that. If you design everything within 1 pixel, the possibility of having a short is very high. And you need to have basically design rules which are specific to the AME materials and the system, because both of those work together to optimize the deposition and the resolution that you're going to be printing with. So if you go with a plus pixel tolerance, you avoid the shorts, but you are at very high risk on the tolerances due to position accuracy, as well as deviation of the drops that could happen as the print evolves and the usage of the printer heads as well as the nozzles continues. So what we see here is the minimum required is at least 2 pixels space and clearance. However, we recommend you typically to use a 3 pixel distance for clearance to ensure basically you have no shorts and a proper define of the electrical material as well as vias and so on. So typically we operate on a recommend operation on a 3 pixel design rules. So based on that, there is a comprehensive set of design rules generated, which are specific to the materials as well as the system itself. And these design rules enable basically the designers to create the circuitry with built-in coils, capacitors, traces, vias, micro vias, and so on, as we will see some examples as we go forward through the presentation. There is extensive information on this, and one of the key things here is the evolution into automating these design rules into the electronic CAD systems, so it facilitates the designer to work within these constraints. So in the case of the Dragonfly system, as we said, we have 2 printer heads, each one jetting the specific material, a stage that moves from one side to the other in the X direction. And then you have the 2 printer heads that will end up deposit based on the software, the conversion of the electronic circuit into the machine language, where basically then injects the inks accordingly. You use a UV to cure the dielectric, and then you use the IR to dry out and sinter the traces, which are based on a silver nanoparticles, and then you end up with a circuit, working on circuit at the end. So on the AME technology, let's clarify, it is not FR4, it is not FR5 or Rogers or Mectron dielectrics. It's not bulk copper. It's not laminated fabrication. It's not constrained by perpendicular designs. It's not constrained by the PCB design rules. It's not limited to D and 2.5D. It's not an IPC defined standards for fabricated boards, except that we'll see some of the standards that do apply to the AME technology, because there are many of them that are already applicable, and there is no need to generate necessarily new ones. The AME technology is a selection of materials to enable 3D electronics, including the electrics, conductors, resistance, sacrificial support, a continuous build body, so it's a single body as opposed to lamination. It's a green process, no drilling or electrochemical plating waste, unlimited structures from the 2D all the way to 3D, and we see some examples. However, it's a very integrated fabrication equipment between the materials, dispensing, algorithms, software, and process and monitors. Basically, the position of these materials, especially the simultaneous ones, you need to synchronize all the components of the system so that you don't mix the two inks in the middle of the process. So you get very well-defined traces and insulating layers. So from standards, basically, we have quite a number of them already in place, which are applicable to AME and should be used in the AME, from the ECAD, not only from the IPC 2581 and the file standards that have been created, the STL and the 3D MCAD. And then there is a number of IPC, ASTM, and IEC standards that apply to the material size. For example, we need to make sure that the emissions of the materials are similar, if not identical, or at least the limits, so that it allows to be used on the different environments where the electronics are being used today, including in space, as well as the reliability standards, how do we test to ensure the functional and the life test of the circuits. Example of functional AME devices. We can start with the antenna for surface acoustic wave. It's a work that was developed by the Italian Institute of Technology for some medical sensor devices. And this is actually now they spin off that as part of a commercial company where they use the AME technology to optimize the communication and the sensors being used here. And this graph shows basically how they optimize the thickness of the dielectric as well as the thickness of the traces, so that the impedance for the sensing, the RF sensing, is optimized accordingly to the design requirements for this particular sensor. Another example can be seen here on work being done by the University of Technology in Sydney by Dr. Yang and his group, where they created a multi-layered patch antenna, where in this particular case, they have 4 units with 3 layers of metal and a single feed of signal. And they basically create the shape. So you can create the shape and modify the shape by selecting different structure or different shape of these antenna elements, or you can also bias the antennas differently and separately, and then therefore fine tune the frequency as well as the shape of the linear polarization as well as the circular polarization. And this, we are talking here about something which is of the order of a couple of millimeters inside and be able to be integrated within the entire circuitry. Another example done also by UTS is this bandpass filter operating at 12.5 gigahertz with a 40.8% bandwidth. And you can see on the left-hand side the actual structure, which is again about 2 millimeters in area total, where you have the quarter resonator inductors as well as the capacitors in place. And then you have the ground plane at the bottom, and then using pillars to bring also the ground plane to the top, all connected, integrated into this system. And we can see here on the hand side, the actual signal data compared to the simulation, which very good agreement altogether for this. So you can figure out here a bandpass filter, which is actually embedded as part of the entire circuitry that is being designed for RF communications. Another example using metamaterials here for terahertz communications, where also the University of Technology in Sydney created this, where you can see here that the antenna gain being operated at, for example, 115 to 125 gigahertz and being quite stable. at around 20 dBs to 21 dBs. Also different aspect conditions, so different design, working 65 to 80 gigahertz and so on. So basically, you have a lot of flexibility of creating these different structures by the AME technology, and quite effectively, as well as not only from the technology point of view and what you can accomplish, but also from the cost and the turnaround, because something like this is basically a couple of days of work on optimization. Another example is this thing done by Rehau in Germany, where they created here a sensor and switch for controlling furniture lighting, where basically by touching on one of the sensors, you select the color of the LEDs or the lighting that they're going to be using, as well as with the scale there, in touching the intensity of the light that is going to be turning on and off. And this is a real 3D structure, as you can see from the exploded CAD view on the left-hand side, where then LEDs were embedded directly into the locations along the axes here shown in this drawing. Example shown developed by Hensoldt, where we see on the right-hand side here is a video showing an actual motor that was printed. The stator was printed, where they have the coils printed, and we see some more examples of printed coils. And then they put in place on top of it a rotor, which a couple of very flat magnets there. Here in the middle, we see a clear example where AME also basically is environmental friendly, because you don't need to drill and cut. You just printed what you need to print, and what you don't need anything, you don't print. So basically use only the material where you need it. And on the far left-hand side is a traditional electronics board, also manufactured by the AME Technology, except that the turnaround for this board is instead of several months, is a few weeks from design to fully testing, including the assembly and whatever waiting time is on the queue. Other examples of technology, for example, we have power transformers or up voltage, as shown in this picture, where we have the coils directly printed inside the board itself, and in the middle, where we don't need anything, there is nothing, it's just empty space there, not printed, and be able to go, in this case, from 5 volts to 20 volts to light these 4 LEDs. Similarly, because we're printing cavities and coils, so now we are working on studying the effect of creating planar transformers with ferrite inserts, cores like the E5 and the E14.5. And this basically enables the creation of planar transformers built into the entire circuitry. An example of the performance can be seen here, where we look at from 6 turns all the way to 24 turns and the inductance, and we can see basically a flat performance as function of frequency that we have tested so far for this type of applications. Another example is printed capacitors which are inside the board itself. And in this particular cross-section, we see 55 layers of parallel plate capacitors embedded inside the board, the electronic circuitry itself. And similarly, we can also make low-pass filters, and we see some of the performance of these devices shortly. But you can see here an X-ray cross-section where you see the capacitors at the bottom of the low-pass filter and the ground plane, as well as the top connecting traces. So looking at the capacitors, these capacitors for this particular dielectric can be designed from a few picofarads to about 3 to 4 nanofarads, with the variation from capacitance to capacitance is less than 1.5%, max minimum with a leakage current less than 1 picoamp. Actually, it wasn't measured because we couldn't get it. It's just very low. Breakdown voltage is over 1 kilovolt, and very important, we can see here the temperature stability factor is very low. It's about an order of magnitude lower than commercially available ceramic capacitors. Also, the Q factor for the AME capacitors Can we be seen here by this lower curve? It's almost essentially doesn't change. It's essentially around 0 along the frequency range compared to ceramic off-the-shelf commercial capacitors. And likewise, basically, if we compare the S11, the impedance factor for the AME capacitors compared to commercial capacitors, we can see here that as we increase the frequency, and we're going here to up to about 6 gigahertz approximately, that the impedance increases a factor of 3 less on the AME capacitors compared to the commercial capacitors. And this is due to the fact that there is no soldering or encasing for these capacitors. So the parasitics are eliminated completely, and you have almost an ideal capacitor in place there. Similarly, we can see the effect here on the low pass filters. This is a low pass filter designed to cut off at 2.4 gigahertz and designed for the AME version. And we can see that the AME version cuts around 2.4, but the signal remains below 30 dBs all the way, in this case, to 20 gigahertz. That was the maximum frequency we were testing at that time. And when we replace the AME capacitors by off-the-shelf SMD capacitors, we can see that after about 6 gigahertz, then stops filtering, which will imply the use of multiple filters to really cut off these other frequencies with commercial capacitors, mounted SMDs. So a clear benefit of the integration of these elements by eliminating the parasitics, so that you simplify the low pass filters for very high frequencies as well. So comparing different structures, and you can imagine that we can print also the shield if it's necessary as part of the design. The shield can be integrated within the electronic circuitry that is being created by AME Technology. We see here the bandwidth in gigahertz of how far, basically, at least until the maximum measurement of frequency for 2.4 gigahertz cutoff and 5.4 cutoff with no shield, as well as with shield. In case of shield, of course, eventually the shield will limit the bandwidth. And we can also see here the weight of the device compared to off-the-shelf version of these devices. And if we compare, for example, this commercial 2.4 gigahertz coaxial low pass filter with its bandwidth similar to the 2.4 shielded, also AME, comparing the 12.5 to 11.5 here, we can see that weight-wise, we have a huge difference, which means that these type of structures are ideal for places where weight is of essence, such as microsatellites, nanosatellites, as well as some other devices, and be basically same performance from filtering the undesired frequencies, but a much lower weight altogether. Moving forward into other structures that can be created, this is a design that enables the integration of vertical integration of ICs, where all the interconnects are basically vertical and lateral within the area of this structure here, as shown by this X-ray. And this basically minimizes the distance between the ICs, and therefore maximizes the speed of the integrated device. So this is basically the ground plane of ground technology for using AME for silicon in package type of designs. Other examples are basically creating side contacts. So if you have a motherboard with some unique performance, but you want to add a specific applications to it, you can create that board printed and then basically insert it into a socket using the side contacts example, or basically go and do embedding of components, like shown in this X-rays or this picture of this particular example, where there are embedded structures here, such as resistors and capacitors, or you can mount them all the way on the side, because being the flexibility of printing, you can basically print a recessed into the board, and then with the side contacts, and insert your passives in there, as shown in this example. Moving forward, looking to the electronics industry roadmap and where the technology will go. So this is an example of an application where AME really creates a unique solution, in this case for power electronics. And this is courtesy of Michael Schiller from Semicron in Europe. And we're looking at the top side view and the bottom side view of a power circuitry, where basically he used AME, and this is only at the design phase at this stage, AME to basically create the spaces here for effective radiation of the heat. So the heat evolution can be done here by these open air channels, and therefore be effective on the structure there, as well as reduce in areas of high creepage, be able to eliminate that by using the advantage that AME technology enables to do that, as opposed to creating using lasers or other techniques to drill these cavities. Other examples that is a technology we're heavily working on is the ability to embed 3D structures, where basically you print the cavities and then you insert your devices, either the contacts at the bottom or contacts on the top, directly printed contacts on the ICs, or eventually some bare dies as well, as shown on the right hand side, where basically we have confirmed the ability to insert the components and print across and have a conduction between the contacts and the chip itself. And this is a technology which is upcoming, and some of the building blocks to develop what we're going to see here as the requirement of the industry roadmap. So the concept that the industry is looking into now is going from the PCB to a 3D heterogeneous integrated system, where as opposed to having the rigid or flex substrate and having your ICs that have been packaged, either BGA or other SMTs, and mounted on here, basically you go directly and shrink the whole thing by integrating all those into the substrate that is being created by AME technology, with the proper interconnects, reducing the total size of the structure and improving its overall reliability. So this is basically the direction the industry is moving forward to use the AME technology. And basically here is a clear example of where the bridge comes between the PCB and the integrated circuit semiconductor industry. As we mentioned at the beginning, the AME is creating this bridge. So examples of this can be done on the formation of chiplets scale modules, where basically it could be for power electronics, like gallium arsenide and silicon on carbide, or the RF and millimeter wave packaging, as in some of the cellular phone systems for system in package of the entire the core electronics, or wireless neural recording, or wireless photonic sensors. All those are requiring the integration of these components to reduce the size, improve the reliability, and be more effective altogether on the packaging and performance of these devices. So if we look at the overall electronics roadmap as created by the IEEE electronics packaging, electron devices, and photonics groups, as well as the ASME and SEMI, and over the period of time. So I've been looking at not only what is being done today with creating only printing, so by screen printing antennas and some aerosol type of things, but starting moving to molding, SMT placement during the process, as we saw some examples here before, as well as then eventually going to die packaging and integration, as we saw in the previous slide. And this is how do we achieve that? We saw some of the elements for that, but let's look at the overall heterogeneous integration with an ideal kind of everything in one single system, where basically we have here not only the substrate with some interconnects, maybe some photonic connections through a waveguide here, and we have the ICs on the top, but we see here basically that this particular stacking of flash memory, RAM, and microprocessor with pair bonding can be eliminated and replaced by the use of the AME multi-chip stacking technology. And that applies not only, oh, sorry, using the wrong button here, applies not only to this particular area, but also to the stacking of silicon in package, as well as we showed you capacitors that basically will do the decoupling between the digital signals and the analog signals. We have the RF technology available already, and moving from here forward. So if we look at the overall PCB type of technology that we described, how it's going to the 3D all in one package, but this is a 3D between 2 to 5 millimeters. There is also a direction of the industry to go to a true vertical integration, true 3D, as opposed to expanding X and Y and shrinking there. Not only do the X and Y shrink, but also start stacking this thing up, anything between 5 to 50 millimeters. And this is basically another area where AME excels into doing things where in this such a device here, you can have a millimeter wave type of antenna stuck on the middle with the RF signal here, as well as the rest of the components below, providing the proper management and shrinking this to a size which basically hasn't seen today yet. So this is basically how we see the technology evolving. And with this, I would like to thank the audience for attending this webinar and open to questions now.
Yeah, we got quite a few here, Jaim. Really exciting. So I will go ahead. In the meanwhile, I will post a quick poll if everyone could answer it, just for us to understand what is your background in the industry sector. It will help us greatly to create material that is more relatable to your vertical in the industry. So please go ahead, fill that out. And Jaim, I think I will start off with the first question. A lot of people asked about environmental tests, or how sustainable our 3D printing process is. What is your general feedback? Do we have any test results that we can share with the public, or is this something that we're looking into?
We have invested on equipment for doing that, and we are starting to do that. We realize that this is different than the traditional electronics PCB technology, because over there you have already some materials which are quite standard. And here basically you have the flexibility to creating different structures and modifying under certain conditions the process. So each variation may create a different strength of the dielectric or the conductive layers. So we have started doing these testings. We have the standards of the equipment into that, and we are using the IPC standard methodology for testing reliability. However, we don't have yet the data available to share. As if we will have, I will have it. I probably will have shown it already. We're in the process of doing that study.
Okay. Then one question was more related to the design or the files themselves. So do you prefer, or do we prefer Gerber type files, or more the AME STP files? Are they acceptable too? So I'm guessing he's referring to the MCAT, ECAT.
Yeah, basically either SL or Gerber today, but we are also working now in being compliance with the new standards from the IPC industry, which will take the ODB++ as well as IDX and others, as well, and continue with the STL, because as you integrate basically electronics into the through 3D, you basically will have to export at the end an STL file. So our products are being evolved to be compatible with all those standards as well.
Okay. Another question is the adhesion between the conductive and dielectric layers similar to that of typical PCB fabrication?
Yes, basically, because this is all integrated and there is no in between any other process steps and so on. You have a very good adhesion. The process also dries out the system, basically by the optimized process, dries out the solvents of the conductive layer, and therefore you have a pure material of the silver in there. Now, okay. Also remember that it's encapsulated and solid within the dielectric, which is basically a continuous block from layer to layer.
Great. I think 2 more questions. We're running out of time, but I would want to assure everyone we will try to follow up with your questions. We we do hope they are valuable to us, and we understand that those are information that you're seeking. So this is something that we're trying to do. I think one good question is also, what is the performance statistics of the conducted in terms of percentage? I know it's hard it always depends on the application itself, but what would you say in general terms?
Let me understand the question. The question is respect to the conductivity of the trace material?
Yeah, correct.
Okay, so the process today, the thin nanoparticles are sintered to about 25 to 30% conductivity related to bulk, and we are developing a methodology and inks that will allow us to go to much higher values, and indicating that we consider a 60% be at least the minimum that eventually we'll need to get to. But that's a material which is under development right now.
Yeah. And then also again with materials, I know you have touched up on this during the webinar, but a lot of people are still asking if there are any other materials that you can either print on, that you can insert or use during the printing process, or how will it look like down the line with printing materials?
Well, the current system has only 2 printer heads, so it's limited to these 2 materials, okay? The capacitors in this particular case that I show, where they use the same dielectric as the rest of the board for its dielectric material. We can see as the technology is accepted and evolving in the future, we may use additional dielectrics. Maybe we'll use also some resistor materials, and as well as some support material to create some cooling channels, as well as we're also looking into what it will take to print with copper. Copper is not an easy material to deal with due to the oxidation properties of copper, but it's a lot of work being done to develop additional materials.
Okay, well, I think that is our time for now, but thank you, Jaim, for setting up this webinar and organizing it so thoroughly, very informative. Everyone else, thank you for participating and joining. We hope we could answer some of your questions. We will definitely follow up with the ones that we were not able to answer, and I wish everyone a great day. Bye.
Thank you, everybody.